Hello everyone, and welcome to today's chem lesson. Today, we're going to talk a little bit more about solubility and how we can tell if a compound will or will not dissolve in water. When we looked at ionic compounds dissolving the other day, we talked about the attraction, this attraction between the positive and the negative ions in the compound, and also the attraction between the polar water and those ions. And we said a compound will only dissolve, an ionic substance will only dissolve if water is strong enough to pull apart the ions. If these attractions are stronger than this attraction. Now, how can I tell just by looking at something whether or not the ion attraction will be stronger or weaker than the water attraction? And the answer is that you can't really tell. You can't just look at something and know which thing will be stronger. And so that's why we have a piece of the reference table dedicated to telling us, are the attractions between the ions stronger, or is the attraction between water and the ion stronger? And that piece of the reference table is Table F. Here we see it in all of its, screenshotted glory, taking up our entire screen. Table F has a couple of different pieces. It's got the first two columns, which act as a set, a small gap to show you that they're not all connected, and then the second two columns, which act as a second set. And what these are going to tell us is whether or not something is soluble, based on the combination of the ions that are there. In the first column, in our main first column, we have ions that are normally soluble, things that normally dissolve in water. And each box is paired with a set of exceptions. We can see that nitrate has no exceptions. There is nothing that makes nitrate act opposite to what it normally does. But something like a halide, when combined with silver or lead or mercury, will form an insoluble compound. It will do the opposite of what it normally does. It's important to see that these are lined up, right? Just because silver makes an insoluble compound with a halide does not mean it will also be paired with a nitrate. Right? You can't just mix and match, right? These are lined up on purpose. Nitrate has no exceptions no matter what. Halides have these 3 exceptions. Sulfates have these 5 exceptions. Right, so the left side, this whole side, tells you things that are normally soluble, and if they have any exceptions, things that would then make them insoluble. On the other side, on the right, this whole chunk gives us the opposite set of information. Things that are normally insoluble, things that normally do not dissolve in water, and the exceptions that make these substances dissolve. Now here we see there's a lot more text in the exceptions column for the right side of the table, but it does overlap, right? All of these contain the same sentence here when combined with group 1 ions or ammonium. There are also unique exceptions, but all of these will be soluble if paired with a group 1 ion or ammonium. And remember, a group 1 ion is anything in that first column of the periodic table. right? It does not list them all for you. So how does this work in practice? Right, let's look at a couple of questions here. Table F still with us, a little smaller, but now we've got some practice problems. Sodium nitrate, NaNO3. Is this thing soluble? Looking at this compound, the way we're going to use Table F is by trying to find the pieces of this compound on Table F. Here we see Na and NO3. They happen to both be on the table. That's not always the case. But sodium is soluble with no exceptions. Nitrate is soluble with no exceptions. So this combination is soluble for sure. What about iron chloride? Is iron chloride soluble? When we're looking to identify if iron chloride is soluble or insoluble, we're trying to find a piece of that compound in the main columns of Table F. On this side, we have neither iron nor chloride, so this is not going to help us. On this side, when we look, there's no iron, but chloride is right here. Chloride is normally soluble, and it will be soluble for most things, unless, right, the only times it's insoluble is if it is paired with an exception. Iron is not one of the exceptions, so this substance is also soluble. The iron doesn't need to be on Table F for it to matter. Right, as long as one piece of your compound, either the positive ion or the negative ion, is on the table, you can discover whether or not it is soluble. How about aluminum phosphate? Soluble or insoluble? Aluminum phosphate is insoluble. When we look, phosphate shows up over here on the side of the table. It is normally insoluble. Aluminum is not one of the listed exceptions, and so it will do what it normally does, which is be insoluble. How about barium hydroxide? Is that thing soluble? Alright, the chat does not fall for my tricks here. barium hydroxide is soluble. Even though hydroxide is in the column where it is normally insoluble, barium is one of the exceptions. And so it does the opposite of what it would normally do, and instead of being insoluble, it is soluble. What about our last one? What about silver chloride? Soluble or insoluble? This is another insoluble compound. Even though chloride is normally soluble, silver is one of the exceptions, which means it does the opposite of what it would normally do. Now, to wrap us up for today, I have a multiple choice practice problem for you, and also a point to make. Here is our question, taken off of an old Regents exam. Based on the full reference table F, which of the following saturated solutions would be the least concentrated? And I have pulled out the relevant piece of table F for you, and I will even be nice to you and give you our compounds here. At this point in the unit, we have not defined saturated or concentrated yet. Right? These are going to come up in later lessons, but that does not mean that you can't answer this question. When you run into a situation like this, where you're looking at a question and you either forgot the definition or haven't learned the definition yet, but they point you to a piece of the reference table, you can play our favorite Sesame Street game, one of these things is not like the other. And in this case, based on reference table F, these three things are all soluble, while this is insoluble. And knowing that the question wants you to talk about table F should be enough to make you think that 4 is the answer here. Right? Now, why is 4 the right answer? Right? What do these words mean? Let's talk quickly through those. A saturated solution is something that is filled. Right? The same way in English you talk about how a saturated sponge is a sponge that is filled with water. A saturated fat is a fat that is filled with hydrogen. And so when we're talking about a saturated solution being concentrated or not concentrated, we're talking saturated solution, a solution filled with salt. And concentration refers to how much of it is actually dissolved. And so when we want something that is the least concentrated, we will take the thing that is insoluble. And we are going to spend more time looking at both of these terms. We're actually going to spend a whole day in our next video looking at saturated versus unsaturated. And we'll spend another day later on in the unit, another video, looking at concentration. But for today, we got through Table F, and I'm going to stop us here to transition into our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.